Well, hello and welcome to the 25th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. So, we just started to look into data driven control and we were trying to address the fundamental question concerning data driven control, where we are given with data and we are trying to identify the model that must have generated the data. So, if you remember, let me go through the symbols again. So, if we have this stands for a data set, and this belongs to the collection of all possible data sets, which of course is a subset of the power set of the universum being the one the set that contains all possible outcomes of the phenomenon that we are trying to model. Okay. And then we had asked this question that okay, can I identify a model B which must sit in a so called model class, that is the class of models that we allow, and we say that this model explains the data, or this model is unfalsified by the data if the data set sits inside this model. Okay. Then we had also defined what is a powerful model. So, if there are two models which both explain the data, say B and B prime, if two models are there which explain the data, both of them, right, that is the data the models, both of them are unfalsified by the data, okay, we say that model B is more powerful than model B prime if B is smaller than B prime. Yeah. Note that this means B is more powerful. More powerful. Why do we say this apparent conflict in the nomenclature, that when B is smaller it is more powerful? Because you see, smaller is more powerful means that it is a better model, you see, because if there is some data, this is the set, and the model that explains it is suppose this set. Now, that means there are so many other phenomena that also are allowed by the model than the data that was there. On the other hand, if we have a model which is like this, then you see it does still have other phenomena inside it apart from the model, but it is still better because it has less other phenomena than the observed data. So, that is why the smaller the model, the better it is. Now, from that perspective, we define what is known as the most powerful unfalsified model. The most powerful unfalsified model sounds like the name of a powerful action packed movie. The most powerful unfalsified model, the MPUM in short, is a model B which of course is unfalsified by the data, and it is also such that if there is any other unfalsified model, if any other unfalsified model is there, then that should imply that this guy, our most powerful unfalsified model, is more powerful than that model. So, that means it sits inside every other model that explains the data. Then we say that is the most powerful unfalsified model. We looked at an example of such a thing when we had data. Suppose our data set D was just a collection of vectors V1 up to V1 up to VR, let us say, which are all n dimensional vectors. Then what is the MPUM for this D? In fact, it turns out to be the span of these vectors. Okay, that is the smallest possible sum. Of course, I did not mention that what is the model class. The model class in this case are all subspaces. All subspaces of Rn. If this is the model class, then inside this model class this B is a subspace, and this is the most powerful unfalsified subspace that contains the given data set V1 up to Vr vectors. Okay. But now you see the existence of an MPUM is not always guaranteed. When is it so that we can always guarantee that there will exist a most powerful unfalsified model? And for that we devise a sufficient condition, although I did not prove it yet. The proof actually is kind of trivial once you think about it, but let me just go through it again. Yeah, I will list out the two conditions and then I will prove it. So suppose the first condition is that the model class is such that for all data set in the possible collection of all data sets, for all such data set there exists a model in the given model class such that the data is explained by the model. There are no unexplainable data sets in the model class. This is first assumption. This is not a very restrictive assumption, as you can see in my last lecture also, that if you just assume that the universum is also a legitimate model, then we have this trivially satisfied, this condition trivially satisfied, because the data set always is going to come from the universum, and the universum is a legitimate unfalsified model for the given data set. But of course it is a very bad model. Yeah, it is almost like saying that, well, whatever think about all possible outcomes of a phenomenon, and you collect that collection of all possible outcomes of a phenomenon, and you say that, okay, that's my model. That's a very bad model, right? Everything is allowed. There is no restriction. There is no restriction that you are putting to your specific set of outcomes that you have in your data set. So it is a very bad kind of a model, but it is a model. Yeah, it is a legitimate model. It is an unfalsified model, but of course a very bad one. Right. Now what is the second condition? Second condition is a bit more interesting and a bit more non-trivial. Okay. The second condition is as follows: for all, notice carefully, sub-model class, that means within the model class, suppose you look at a subclass of models, and then you look at this intersection of all B prime belonging to the submodel class, and you look at their intersection. If this intersection also is a legitimate model, yeah, so that's the second condition, and these two conditions together would imply that there exists a unique B in the model class, which is an MPUM for the given data set. So for every data set there will be a unique MPUM that explains the data, right. Let me just compare this with the conditions that I wrote down in the previous lecture. Yeah, you see the first one says that for every data there is at least one model that explains the data, and the second one is this, that there is this the intersection is also a model. Okay. Now why should these two conditions imply that there will be a unique MPUM for every data? So let me first prove existence and then we will show uniqueness. Uniqueness actually is quite easy. First we show existence. Existence also will turn out to be quite easy because it is just a logical conclusion of what we have done. So now you see, suppose somebody gives me a data D, yeah, whether it is possible or not, I look at this family of all all models within the model class that are unfalsified by the data. That means B is in M and B contains D. So, first observation is that F is non-empty. Well, I should have mentioned something here as well for all non-empty. Okay, this is important. So, F is a non-empty set, at least one element is there. What? This is non-empty because of assumption 1, because of assumption number 1. You see assumption number 1, what does it say? That for every data there is at least one model, and you can satisfy that by assuming that your universum itself is a model, although patently a bad one. But you see, that implies that this family that you have defined is non-empty. That means for every data there will be at least one model that explains the data. Okay? So, now this is a non-empty set. So, this is a subclass. This obviously is a subclass of the model class, because it is a subset of all possible models. So, then this means now if I define my B to be equal to the intersection of all B prime in this family, yeah, then by our second assumption this also is a valid model. This is a valid model. By assumption 2, my bad, sorry. By assumption 2, this is a valid model, because this is a subclass, F is a subclass, and I am looking at its intersection, and therefore, this is going to be a model by assumption 2. But now I claim that this is my MPUM. Why? Why is it unfalsified? Obviously, look at B. Yeah, B obviously will contain D. Why? Because every B prime, that is how B prime has been defined. Every B prime will contain D. So, if every element of this intersection, every constituent of this intersection contains the data D, then the intersection obviously will contain D as well. So, it is unfalsified. Why is it most powerful? Yeah. So, suppose there is a B prime that contains the data. This implies B prime belongs to this family. So, that means this B, which is the intersection, which is by definition the intersection of all B prime in this family. Yeah, to distinguish, let me call one of this as a B hat. Yeah, because this is the collection of all those, it's the intersection of all those B prime which is there in this family. B hat is one of the constituents of this intersection. So, obviously this intersection will be contained in B hat, because B hat is one of the constituents of this intersection, one of these guys whose intersection is defined as my B. So, therefore, B must be most powerful unfalsified model. That shows existence logically. In fact, if you see, we have done nothing more than what we did for this example. You see the span, I had given it to you as an exercise, that this span is nothing but, this span is nothing but the intersection of all those subspaces, that contain this set of vectors. Given a set of vectors, the subspace spanned by those vectors is in fact the intersection of all those subspaces that contain that collection of vectors. So, like exactly same logic is followed when we are showing existence of an MPUM. What we are doing, the trick basically is looking at the intersection of all unfalsified models, right. and then uniqueness will follow automatically, because if there are two models B1 and B2, two models, both are MPUM. So, B1 and B2 both MPUMs, suppose, then because both are unfalsified, B1 contains the data, B2 contains the data, because B1 is MPUM. This would imply B1 will be contained in B2, and likewise because B2 is MPUM, this would imply B2 is contained in B1. So, we have both containment together, we must have B1 equal to B2, that is it. So, uniqueness in fact immediately follows. So, now the point here that we are trying to make is that for the existence and uniqueness of an MPUM for a given data, we must have these two conditions. First, if we look, remember these are sufficient conditions, by the way. So, even if they are not satisfied, it might so happen that you still have an MPUM, but at least if you have these two conditions satisfied, 1 and 2, then you know theoretically that there will exist an MPUM for every data. The point is that this is not the method to be used to construct an MPUM, as we will see very soon. This will just give you the confidence that there is an MPUM. So, now let us test these two conditions to the scenario that we have been interested in, namely linear time invariant systems. So, suppose now we have linear time invariant systems, discrete time, yeah, and in that discrete time systems we are also going to look at systems defined over the positive real line, the positive integer line, right. So, my indexing set here is Z plus. I will give it to you as an exercise to prove it over Z. So, now look at this T equals Z plus, and I had said that the operator ring in this case is R sigma, which will also write as R xi, and it will be understood that this xi stands for the shift operator sigma. Okay, we have defined this shift operator as the left shift. Now, so I wrote Li, I should write LTI systems. Okay. So, now what sort of data are we expecting? Data set. A data set typically would be a collection of trajectories. For example, it could be just one trajectory, it could be W0, W1, W2, W3, this sequence, yeah, which is a data where each of these Wi's is a vector of size RQ. So, essentially what we have is one particular trajectory, is one sequence, one vector valued sequence, one trajectory. Okay. With this data we would like to get whether it is possible to get a behavior. So, what we mean by a behavior in this case? A behavior is a linear time invariant system now given by linear time invariant system, which is given by a system of ordinary difference equations, that is in shift with constant real coefficients. This should ring a bell with you because these are the kind of systems that we have been looking at so far, although of course, we looked at continuous systems where we had differential operators as opposed to difference operators, but there also we had ODEs, ordinary differential equations, right. So, typically just look back at your earlier lectures when we were dealing with descriptions of systems in kernel representation and so on. What we are typically looking at here is basically all those. So, what is my model class? Model class contains typical behaviors which are given by kernel representations of polynomial matrices R sigma, where R xi as before is a P cross Q or G cross Q, we will say P, does not matter, is a polynomial matrix, is a P cross Q size polynomial matrix. That is my model class. Yeah, this is like almost all linear shift invariant systems that we deal with in engineering problems are basically given by kernel representations of such polynomial matrices. Of course, you have to remember that the indexing set is Z plus, otherwise these matrices will be LoRa polynomial matrices. Okay. If T is Z, then these matrices will be LoRa polynomial matrices, that is the only difference, and similar analysis will be true for those kind of systems. I will give those as exercise problems to you as promised. Now, the question is, given such a data set which is a collection, which is either one single trajectory or a collection of trajectories, yeah, basically D is a subset of the universum, and the universum is actually all possible trajectories, namely T raised to the power of Z plus, sorry, Z below plus, Z plus whole to the power Q, which is also the same as R Q whole to the power Z plus, right. So, this is a data, this is a typical data set that we have here. That is, it is a collection of trajectories. Each element of this set is a trajectory, and D is such a subset of this. That means it contains one or several trajectories. Now, the question is it possible to find out a, and that way unique, the most powerful unfalsified model. That means B is in D, yeah, B contains D, and if there is any other B prime which is also unfalsified, then that should imply B is contained in B prime. The question is, can we guarantee, is it true? Remember, what do we mean by B, B prime and so on? All these B's are given by kernel representations of polynomial matrices. So, in a way what we are asking is kernel of polynomial matrices. So, in a way what we are asking is that given a collection of trajectories, is it always possible to find out difference equations, a system of difference equations that explains the data? That means the data satisfies these difference equations, and if there is any other system of difference equations that also makes that also these trajectories satisfy, yeah, those system of equations generate a smaller module compared to the system of equations that we have seen, right. So, that means, in other words, we are asking, do we have the largest possible set of equations, the largest possible system of equations, or the model of equations that this B satisfies? Is it possible? Yeah, this data, not the B, the data satisfied. So, given a collection of trajectories, is it possible to find out the largest possible system of equations that this D satisfies? Does such a thing exist? And of course, if it does, it will be unique by automatically. But the question is, does it exist? So, we can, to answer this question, we can go back to our theorem that we proved, and we can ask, does 2 and 1 are assumptions 1 and 2 satisfied in this model class? The answer is yes. 1 is immediately true. You see, 1 is immediately true. Is the universum a legitimate model? Of course it is. What is the universum? The universum in this case is r q to the power w to the power z plus w to the power t, that's z plus. Is it a model? What equation does it satisfy, this universum? Of course, this u is nothing but kernel of the 0 matrix. Yeah, it's kernel of the 0 matrix. No equations whatsoever. So of course it's a model. This 0 is a very special equations, right? It's a special system of equations. So of course it's a legitimate model. So 1 is fine. What about 2? Any subclass M prime of my model class, and then I define this intersection of all B primes that are in M prime, and I look at this B prime. Is this also a legitimate model? To translate this into the language of equations, polynomial equations, what we are saying is that, suppose, okay, so first understand this. Suppose I have a B1 which is given by kernel of R1 sigma, and a B2 which is given by kernel of R2 sigma. Notice that this R1 and R2 both are polynomial matrices, and importantly they must have the same number of columns but possibly different number of rows. Yeah, possibly different number of rows. Why? Because the number of rows tells us how many equations do I have, and number of columns tell me number of columns tells me that what are the number of variables, number of manifest variables here. And because we are talking about one model class, and that model class has this q fixed, right, r q to the power z, right. Every model should explain data coming from here. So that means those models must have exactly q number of columns. So that is why these matrices have exactly q number of columns but arbitrary number of rows. Now tell me, let's think about it. What is a kernel representation for B1 intersection B2? B1 intersection B2, if you think about it, must be given by kernel of this matrix, no, R1 sigma and R2 sigma written one after the other, does not matter the order, but just write one after the one below the other. Why is that so? Because you see, any trajectory that must be in B1 intersection B2 must satisfy equations coming from R1, and in addition it must satisfy equations coming from R2, because it has to be there in both B1 and B2. So to impose both equations, all you have to do is that you just write them one after the other, all these equations, you list out all the equations. Okay. So then, given any subclass of such things, all we have is actually a subclass of R sigmas. So the question in terms of equations will turn out to be the following. In terms of equations, it will turn out to be as follows. Yeah, assumption 2, in terms of equations, it will follow that given a collection S of R sigma, where R sigma is a polynomial matrix of q columns and arbitrary number of rows, yeah, and then you look at this big matrix. I am doing a little bit of abusive notation, because I cannot write, when I am writing it like this, it appears as if there is this list, this collection of polynomial matrices is enumerable, but they need not be enumerable. Yeah, it's just it's just that It is just that I am writing all the equations, all possible equations one after the other. For you to understand it, I am just writing them as if they are enumerable, but in general they need not be enumerable, right. Is this a legitimate polynomial matrix itself? That is the question. So, if you look at a collection of such polynomial matrices and then write them down one after the other, if it is possible, yeah, you write them down one after the other, is this also a polynomial matrix? If it is so, then assumption 2 is satisfied. But now if we use a little bit of sophisticated language, we can notice the following. You see, when I write two polynomial matrices R1 xi and R2 xi one below the other, and then look at kernel representation, what I am really trying to understand? I am really trying to understand the module generated by these two. That is what defines the behavior, right. The module, the sub module that these rows generated by the rows, is the one that governs the behavior, the system of equations. You see, we have already seen before, although with continuous systems, but you would have proven using your exercises that for discrete systems as well, it is the module that matters. It is the module that is uniquely associated with the behavior. So, here also if I am interested in this behavior, I am actually interested in this sub module, the row span. So, in that language, what we are really asking is that if we have a collection S of these matrices of arbitrary number of rows, but q number of columns, look at these guys and look at the submodules generated by them. R is the row span of this given polynomial matrix. What we are asking is that if we look at the sum, you see the row span of this is in fact, so here row span of R1 xi and R2 xi is in fact R1 plus R2, the sum of these two submodules, sum of this row span and this row span. Yeah, something, every vector that can be written as a linear combination here plus a linear combination here, that is it, this is the one. So, that means what we are doing here is we are asking this question that look at these subspaces. So, for the sake of understanding, I am going to write an Ri here, which is meant by, I will explain what this is, I in I. Is this also a submodule of this? What is I? So, I, by I mean the following, that this was my S, no? S is the collection of all those R xi's, sorry, dot cross q xi some property. What I am saying is that here I am actually I am using this to get this subfamily. I am not assuming that this is some countable infinite set or countable set, this is some arbitrary set, some indexing set. Yeah. So, this is the question that we are asking, is this a submodule? The fact that it is a submodule will immediately follow, and then a very special property of polynomial and polynomial ring and the modules generated by modules of a polynomial, finitely generated modules of a polynomial ring, namely the property of Noetherianness, is something that will guarantee that I will always have a polynomial matrix which will give me the intersection of the behaviors. Yeah, this and more consequences of this is what we will see in the next lecture. Till then, take care.